Hello everyone, my name is Oren Shroot from the Technion, Israel Institute of Technology. Today I will present our paper, SFMNet, Sparse Focal Modulation for 3D Object Detection. In this work, we address one of the critical limitations in modern LiDAR-based detection, efficiently capturing long-range dependencies in sparse 3D data. Current state-of-the-art detectors generally fall into two categories. First, we have sparse convolution detectors, shown in row A. These are highly efficient but suffer from limited receptive fields. Second, we have transformer-based detectors, shown in row B. While they capture global context, they come with quadratic computational complexity. Our goal was to design a network that combines the best of both worlds, the long-range modeling of transformers with the linear efficiency of sparse convolutions. Why is this long-range context so important? LiDAR data is inherently sparse. As you can see in this example, a few points on a distant or occluded object might look like noise. Local features alone are often insufficient to distinguish a vehicle from background clutter. To correctly identify these objects, the network needs context from the surrounding geometry, for example, the road plane or nearby structures, which may be meters away from the object itself. To solve this, we introduce the Sparse Focal Modulation Module, or SFM. Unlike standard self-attention, which calculates interactions between all query key pairs, leading to quadratic cost, SFM constrains interactions to a few hierarchical focal contexts. This allows us to capture global relationships with strictly linear complexity, making it scalable to large, high-resolution 3D scenes. Here is how the module works internally. Instead of dense large kernels, we use a stack of submanifold sparse convolutions with small kernels but progressively increasing dilation rates, typically 1, 3, 5, and 7. This hierarchical design allows us to rapidly expand the effective receptive field at each level, capturing wider and wider context without exploding the parameter count. Crucially, not every object requires the same scale of context. We employ an adaptive gating mechanism, denoted here as GL. This allows the network to dynamically weight the contributions from different hierarchy levels. For small objects, it may prioritize lower, local levels. For large or occluded objects, it can attend to the higher, long-range levels. We integrate this module into SFMNet, a fully sparse 3D detector. The backbone consists of 4 stages. In each stage, we use SFM blocks to establish a wide receptive field, followed by sparse residual blocks to deepen feature extraction. Unlike many competitors, we maintain full sparsity even in the 2D backbone, ensuring maximum efficiency throughout the entire pipeline. We evaluated SFMNet on 3 major datasets, starting with Argo-Verse 2, which is challenging due to its long detection range of 200 meters. As shown in Table 1, SFMNet achieves a state-of-the-art map of 40.4%, outperforming recent methods like HeadNet and SAFDNet. We see particularly strong gains in smaller classes like pedestrians and bicycles, validating our model's ability to use surrounding context to detect small, difficult objects. We also tested on mid- and short-range datasets. On Waymo Open, shown on the top, we outperform transformer-based methods like DSVT and PTV3 on the difficult level 2 metric. On new scenes, shown on the bottom, we achieve the highest map among sparse detectors. This demonstrates that our long-range architecture generalizes well and does not sacrifice precision in shorter-range scenarios. Efficiency is a key contribution of this work. In Table 4, we compare our module against global and local attention mechanisms. While global attention quickly runs out of memory on large grids, and local attention limits the receptive field, SFMNet achieves higher accuracy than both while maintaining a low memory footprint due to its linear complexity. The impact of this design is visible in our qualitative analysis. Given an input scene on the left, we show the ERF with and without our SFM module. In the middle, without SFM, the effective receptive field, color-coded from blue, outside ERF, to red, high attention regions, is restricted to small fragments of the vehicles. On the right, with SFM, the network successfully aggregates context across the entire object surface. This allows SFMNet to confidently detect partially occluded vehicles that the baseline model misses. To summarize, we presented SFMNet, a new 3D detector that enables long-range dependency modeling without the computational cost of transformers. By leveraging hierarchical sparse convolutions and adaptive gating, we achieve state-of-the-art performance across multiple datasets, from short-range urban driving to long-range highway scenarios. Thank you for your attention. Our paper and code are available in the shown links.